I am Jeremy Fairbank, also known as El Papapoyo on Twitter, and today we're going to talk a little bit about Elm. So just a little briefly about me. I work for TestDouble as a remote software developer and consultant, and we believe that software is broken and we are here to fix it. So our mission is to improve how the world builds software, and we do that by not only working alongside your team and helping you get stuff done, but also to help your team grow and improve and how you function and work together. So if you're interested in learning more and how we can help your team improve or just to help you get some work done, please say hello at testdouble.com. So although this talk is about Elm, I firmly believe it is also about developer happiness. Now there are a lot of factors that define what make us as developers happy, and I don't want to make light of them by any means. However, I think that the tools that we use day to day can greatly impact and drive our happiness as developers. Many times we have to invest a lot of effort in doing our work. A lot of mental burdens come from activities like making sure we call functions with the right arguments, make sure we handle errors, and make sure we check for null and are we handling it properly. So this can make us feel a little less confident that we understand everything going on in our applications and that it will run properly every time. So we would like to have tools that empower us and make us more productive. Our tools should make it easier to write code, it should make them easier to refactor that code, and it should make them easier to write tests. Our tools should really make us feel confident by having our back, and therefore make us productive. By making us productive and confident, we can focus on our domain a whole lot more and then achieve greater developer happiness. I believe that this ideal world is possible with Elm. So Elm is a functional, statically typed language that compiles to JavaScript, and it's primarily a web and UI-focused language, which makes it really ideal for building front-end applications. I believe Elm matters for many reasons. So one of Elm's greatest benefits is that there are no runtime exceptions in practice. How many times have you had an exception crop up in production or during runtime that you didn't expect, and then you have to track it down and figure out where the bug's occurring? Well, in Elm, errors are going to occur at compile time, and it's going to provide to you helpful error messages that let you find the source of the issue and quickly fix it, so nothing's going to crop up for your users in production. All this is possible because of Elm's strong static types. There's no undefined is not a function. In Elm, null and undefined really just don't exist. So that helps prevent a lot of subtle bugs and issues like null reference errors. Instead, Elm provides powerful types like maybe that, along with the compiler, ensure that we do handle null-like situations in a safer manner. Elm is actually very fast. It easily competes with frameworks like React, Angular, and Ember. In fact, in certain scenarios, Elm actually outperforms them with and without optimizations. And this is largely possible because of Elm's runtime and virtual DOM rendering. Finally, Elm has one framework that is built in, and it's called the Elm architecture. So there's no fatigue about which framework do I need to select, which libraries do I need to add on top of that. It's all built in with Elm. And the Elm architecture allows you to sensibly organize your code to give you predictable applications via the model view update pattern. So with that introduction out of the way, let's start to really look at Elm a little more, learn why it matters and how it drives developer happiness. And along the way, we'll learn some of Elm's syntax and how we can build simple applications with the Elm architecture. So first and foremost, Elm is a functional language. And functional programming has become quite a buzzword these days, but I believe it's really important, and let's just distill it down to what really matters. It's programming with just functions. Functions are easy to write, and they're easy to understand. So here's how we can define functions in Elm. This is a simple Elm function definition, a greet function. It takes a name and it returns a string hello name. So in Elm, when we define these functions, we provide an identifier, and then we provide arguments, but we just use white space. We don't have to worry about parentheses and things like that. So it's a very minimal syntax that allows you just to focus on writing your code and defining the function very easily. So you can ramp up on Elm's syntax pretty easily. Every Elm function, we just set it equal to a single expression. So there's no concept of multiple statements and then some return keyword. Instead, everything is just a single expression, and this helps us focus on writing smaller functions that do one thing and do that really well, and that way we can easily understand our code. So we see here in this example, Elm has strings, we use double quotes for our strings, and then we can concatenate hello and name via the concatenation operator, which is the double plus symbol. To call functions, we do something a little similar. So when I want to call my greet function, I use white space again to invoke it and pass in the string Fluent Conf, and then I can get back hello Fluent Conf. And then down here, what I have, these double dash, are just how we do comments in Elm. Now functions in Elm are also pure, and so purity, it's another buzzword from functional programming, but it really is important and has great benefits. A pure function is simply a function whose return value only depends upon its arguments. That's data in, data out. There are no side effects. We don't depend upon global state in Elm. So what I mean by side effects are things like making an HTTP request, changing some global state, or printing to the console. But really the upshot of having this purity principle is that we can look at these pure functions and we can easily know what is going on and what's happening because they are very predictable. And every Elm function has this guarantee. So if we build Elm applications out of pure functions, then we can say our Elm applications are predictable and we can trust them more, especially when we go to refactor our code. Pure functions are also easily testable because it's just a simple unit test. When I pass in a certain value, I expect to get back a certain value. So just to put that in terms of Elm functions, let's say we have a different function, an add function. In this case, it takes 2 arguments. And again, we just use white space to delimit these arguments. But it's a pure function because its result, x plus y, only depends upon those arguments. It doesn't depend upon any outside state or make any side effects. And the guarantee then is that I know if I call add with 2 and 3 here, it's going to add those and always give back 5. And I can easily test that, I can easily trust that, and that is every Elm function has this guarantee. Elm is also a very expressive language. We already kind of hinted at that when we said functions have a single expression for their function body. But this leads to very terse and declarative code. And kind of the upshot of that is we can write less code to do more. So we don't have to write as much code as we might have to do in JavaScript. And hopefully by writing less code, that means we have the less potential for bugs to crop up in our applications. So here's an example of what all that means to have expressive and declarative code. So Elm also has data types like lists. These are very similar to JavaScript arrays. So we use the normal brace syntax. We have 1, 2, 3, 4, 5 in this array. And it's a little different from a JavaScript array in that it's more like a linked list than something you can index into like a JavaScript array. So lists are really built for iteration, mapping, filtering, things like that. So what I want to do in this code is I want to double every number in that list. So take every number, multiply it by 2, and return a new list. So I can do that very easily with expressive declarative code. So I have this helper function called double. It takes an n, and it returns n times 2. Very straightforward function. And then I can have this double numbers function that takes a list, and then it's going to double every number in the list. And we do that through a built-in helper function from Elm's standard library, list.map. And maybe you're familiar with this already from JavaScript doing map over an array. But it's going to take 2 arguments, a transforming function and the list to transform. So double is our transforming function. And what it's going to essentially do is Elm is going to take care of all the details of applying that function to every item in the list and returning a new list for you. You don't have to worry about handling that process. So you can write less code to achieve just the same amount as you might have to do in other languages. And so we can call that with my list, and I get back 2, 4, 6, 8, and 10. So that's the idea of being expressive and declarative, that I can write less code, but do still plenty more with it. Elm also has auto-curried functions. And warning, another buzzword, but the idea with curried function is that Elm functions are inherently great building blocks. I can write very general, small functions, and I can make more complex functions out of them because they are curried. So to understand this curried concept, let's look at that add function we had earlier again. When I call add with 1 and 2 here and I get back 3, I'm not really passing in 2 arguments at one time. Rather, I'm passing in 1 argument at a time. So Elm functions only take in 1 argument at a time. And every time they take in an argument, if not all the arguments are satisfied yet, it's going to return back a new function where we've essentially pre-filled the argument that was passed in. So what's really happening here, when I call add with 1 and 2, it's as if I wrapped add with 1 parentheses to denote the fact that I'm returning a new function here. And that new function gets called with 2. So when I call add with 1, I'm pre-filling in the x argument to be 1. That's called partial application from functional programming. And when that x is pre-filled, when I call that new function with 2, then I fill in y, and then all the arguments are satisfied so I can return the final result. But the benefit of that is that now I can take the very general add function, and let's say I want to just write some toy function increment that takes its argument and adds 1 to it. Well, instead of having to write the increment function, I could use the add function, call it with 1. I know that it's curried, so it's going to fill in x and give me back a new function. And then I can use this increment function without having to write its explicit definition. And so expand that out to larger applications where you can have lots of these general functions and build more complex functions out of them. And again, you're having to write less code to still create very complex applications in Elm. So another very useful feature with Elm is this idea of piping. And it's a way to deal with the issue of if functions have to have a single expression, what happens when I need to call multiple functions to produce a result? Well, we can achieve this through something called piping. So to understand the problem here, let's look at this example. I have that greet function we had earlier. It takes a name and it concatenates that with hello to give me hello name. I have another function called exclaim, which takes a phrase and just appends an exclamation point to it. But let's say now I have some complex function that needs to take a string, convert it to uppercase, then pass it into greet, and then pass it into exclaim. Well, I'm going to end up with some very lispy looking code where I have to do a lot of parentheses wrapping. And so that kind of defeats the purpose of Elm really being a very readable, terse language and makes it harder to understand what's going on here. But we can counteract this particular issue by using piping. So Elm has this really great operator called the pipe operator. And it's kind of like function composition if you're familiar with that. But the idea is I can take some value and I can chain it through multiple function calls. So it's kind of like if you're familiar with Unix shell programming, how you can pipe one command's output to another. So whatever's to the left of that operator will become the argument to whatever function is on the right. And so then I can write this in a more readable manner where I can clearly see that I'm taking this string, I'm converting it to uppercase, I'm passing it into greet, and then I'm passing it into exclaim. So it's as if it gets shifted down and piped over there. That gives me this uppercase string Tucker. That gets piped through then to greet, and then I get hello Tucker. And then finally that gets piped through to exclaim. And it gives me the final result, hello with Tucker uppercase and the exclamation point. But the nice thing about this is that I can write functions from smaller functions, and I can piece them back together with this readable syntax via the pipe operator. And it's kind of like doing method chaining in JavaScript, where you would have an object and you just call multiple methods and chain them on down. So I want to return back to the benefit of no runtime exceptions in Elm and kind of discuss how is that possible and what can we use to accomplish that. So I had mentioned at the beginning of this talk that Elm is a statically typed language, but I hadn't really talked about types yet. And that's because Elm can actually infer static types in your program. However, Elm strongly prefers that you do provide type annotations for a couple reasons. It's good for documentation, so you and your team can look at the code and expect and know what particular values and functions types are. Also, if you provide types and the Elm type checker infers something different, it can provide hints to you about somewhere you might have an issue in your codes where you can fix your types. So we have some basic values. We've already seen some. We have integers, we have strings, we also have booleans and lists. And to do a type annotation, we just provide the identifier and then its type, and then separate that with a colon. And we just usually put that right before the actual instantiation of that value. So we have int, string, and bool here. And notice with list, we also have list int. So lists have to always contain one type inside them, and that's important for the type checker. So I can't put a string inside this list of integers, but I could create a separate list of strings. And so I type this by saying list, and then providing the value or the type of whatever values are inside the list. And that's something we call a type variable. So where I can have a list of integers or a list of strings and so on. Now as far as functions go, when I want to provide type annotations, it's a little different. We introduce the arrow here. And what it's saying is that greet takes a string, and then the arrow says it maps to or returns a string. And that's how we kind of can read that. But add's a little more tricky. So what's going on here? We have two arrows. What does that entail? Well, what's really happening here, remember Elm functions are curried. We say Elm functions take one argument at a time, and they keep returning functions until all arguments are satisfied. Well, that's what this type annotation is even saying. It's saying I take an int, and then I return a function that takes an int, and that function finally returns an int. So if that's a little confusing to read at first, you can write your type annotations like this, where I can explicitly wrap that in parentheses to say this takes an integer and it returns a function that takes an integer. But what's all the benefit of having these static types? Well, what happens if I go to refactor some of my code, and I've done a lot of changes, and I'm accidentally now calling the greet function with a number for whatever reason? If this was in a JavaScript code base, you might run into potentially a type coercion issue, and you may not catch that there's a bug immediately, or you might get a runtime exception. Well, that's not going to happen in Elm. When I try to compile this code, it's going to fail. It's going to know you're not calling functions with the right type of arguments. And so this code will never end up getting to the user until you've fixed it. And so that's one big benefit of having these strong static types in Elm. So the next thing Elm provides is all data types are immutable. And what I mean by immutable is that I can't change values in place. I can't mutate it, as we call it. So take a JavaScript object, for example, and it has multiple fields, and say you want to change the value of some property. Well, that's possible in JavaScript, but it isn't in Elm. And so to understand why that's important and how do we do immutable changes in Elm, let's introduce the record type. So the record type in Elm is kind of like a JavaScript object. It's a way of collecting different properties together and values within one data type. So in this case, I have a dog. It's a record. And for the record type, I provide the curly braces, very similar to the JavaScript object, and then the properties contained in it and their types, string and an integer for name and age. And then for creating a record, I again use very similar curly brace syntax from JavaScript. And I provide the key value pairs, name and age, and I use equal sign instead of colon, so it's pretty much like a JavaScript object. And also like a JavaScript object, I can access the properties in it with the .record syntax for accessing fields on the record. So I can grab name and age out. So when we talk about immutability though, what if I want to change the age on this dog? I want the dog to have a birthday, and now I want his age to be 12. Well, how do I go about that if I can't change the value in Elm? Well, the thing with immutable data is instead of changing state, you want to create new state or create new data. And the benefit of that is now you're going to have an explicit flow of data in your program. You don't have to worry that some random function is mutating data. You always know that it has to produce new data, and that's going to come out in the open to where you can take the data and pass it off to some other function. But you don't have to worry about any mutation bugs occurring. So I can write my haveBirthday function. It takes a dog, and it's going to return a new dog with its age incremented by 1. But one tricky thing is we have to essentially copy the original dog, keep all of its original properties, and that could get cumbersome. So Elm does offer a way of doing that. So this is kind of like object.assign or the spread operator from ES6 and beyond in the JavaScript world. But what this syntax lets me do with the curly braces and then that bar that's kind of in the middle is it's a way for me to copy one record and then overwrite any fields in the new record that I'm creating. So I'm saying copy the properties in dog and then override the age in this new dog to be the original dog's age plus 1. So to use it, I create my dog, same name and age as before, and then I create an older dog by calling have birthday on that dog. And it's going to produce a new record again. We're not mutating that original record. So I get back a dog. I have age is now 12, so he had his birthday, and name is Tucker. And I get the name there because it knew how to copy the original record and keep those original properties around for me. I didn't have to explicitly handle that. And again, this is immutable, so I don't mutate that original dog. It still has the same age and name as before. So now moving along, another useful feature in Elm is that we've seen types. We can actually create our own types, which is very useful when dealing with domain-specific code. So whatever your domain for your product or whatever you're working on, you can create your own types and represent them in your program, which makes your code a lot more readable and documentable, if that is a word. So there's a couple ways we can create our own types. One way is we can create what's called a type alias. So that dog record we had earlier, it could get cumbersome to rewrite that record syntax for the type every time. So I can actually create a new type called dog, and this is uppercase, and I can say alias this to a record type that contains the name and the age. And I'm also including a new field called breed. So that's one way we can create a new type, by aliasing it to some other type. Another way is we can create an entirely new type with its own values. And this is something called a union type. And this is something that really helps Elm shine. So I want to represent the breed of my dog, but I don't want to use a string or something like that because I could let bad data get in there. Rather, I want to use the compiler to basically block what values are allowed to be used with the breed type. So in this case, I'm just going to say it can be a Sheltie or a Poodle. And that's how we use this union type. It's a union of different values. So it's a type breed, and it can take on either the value Sheltie or Poodle, and that's it. And the compiler will ensure I can only use those values. So to utilize this, I can declare my dog to be of type uppercase dog. And then when I create the record, same as we saw before, but now the breed, I'm going to use that Sheltie value. And I can't use anything but what's allowed within that breed union type. And the compiler, again, will ensure I can only use those values. So one of the other things that I mentioned earlier is that there is no undefined, it's not a function, there is no null in Elm. But there are obviously going to be null-like situations, so how do we deal with that in Elm? Because it's going to eventually happen, especially if we're fetching data from some API. Well, the way we handle it is with a special union type called maybe. We saw the union type with breed, it had two values. Similar with maybe here, it has two values, just and nothing. And so let's kind of unwrap what these values mean and how we utilize that to represent null in our programs in a safer manner. So these values just, if you think of an operation where I can return a value or I can return null, I can represent that value with this just, and I want to wrap it. So this union type, with its values, I can also wrap data inside those values. And so this just is a way of wrapping a successful value, like if I wanted to get a user maybe out of a dictionary or something. If I successfully get it, it'll be wrapped in this just. If I don't get that user, it's a null, then I can represent that with this value called nothing. And so this is very similar to null, but we'll find out why it's more beneficial than null in a second. And then just a little aside, this a here is a type variable. I mentioned that earlier with lists, but it's a way for me to say that this maybe type can contain whatever could be in the just. So it could be maybe of an int, maybe of a string, just like we had list of an int or list of a string. And a good way to just think about this type is we could say either I have just the value a or I have nothing. So to utilize this, I could have, say, a divide function that's going to divide x by y. We know we can't divide by 0, so we'd like to represent that in some meaningful way. It's a null type situation where I can't really represent this any good way. So my function is going to return maybe of a float. So maybe I have a float or maybe I have nothing. And then I'm going to use an if-else expression. We haven't seen those yet, but it's essentially like a ternary. So if-else, there's not an if-else statement, rather it's a single expression, again, like a ternary in JavaScript. So if y, which is my denominator, is 0, I can't represent that. I can't do that division. So I'm going to represent that as a null with this nothing value. Otherwise, if I can successfully divide it, then I'll do the division, and then I'll wrap it in that just so I can actually get the real value out. So if I call divide with 4 and 2, I get just of 2. If I call divide with 4 and 0, that's a null-like situation, then I'm going to return nothing. But I'm still dealing with null here, so what is really the benefit of Elm if I still have a null? And how do I even get that 2 out? Well, I can use something called a case expression. And it's much like a souped-up version of the switch statement from JavaScript. But again, it's an expression, so it'll always return a value. So I provided some expression to match on. In this case, the result of divide by 4 and 2. And then inside it, I can have branches. If I'm it's called pattern matching when I use this case expression. I'm matching over this value. If I'm using a union type, I can match every value that that union type represents. If I match on just, I can bind that wrapped value, which was the quotient or the division value, I think it's quotient, and I can bind that to n and then return that in a string. Otherwise, if I don't bind that and I'm dealing with the null, then I can handle it here. But here's the real benefit of going through this process of having to pattern match with this case expression. If I comment out nothing, or if I forgot to handle it, and I try to compile, it's not going to compile for me. It's going to throw an error at the compile time. And it's going to be because Elm knows when it pattern matches on these union types, it knows what all the possible values are, and it knows if you're not handling one of those values. So this is essentially making sure you do handle the null situation. So now I can trust my code that I don't have to worry, is there a null here, is there a null here? The compiler will ensure to tell me where are there nulls and are you handling them, because it won't let it compile if I'm not. That's the real benefit of dealing with maybe in Elm. And finally, I want to shift gears now to start looking at how you approach building applications with Elm and talking about the Elm architecture. So I mentioned there's no worry of fatigue in Elm because you have one architecture already built in, and it sensibly organizes your code via the model view update pattern. So all your state is going to be consolidated in this model. Your view layer is going to be responsible for displaying that state. Your view layer and other sources can produce messages, which are kind of like actions from the world of Redux if you've used it, that you're going to use to describe how state should change in your program. And that message, along with whatever the current state is, will be fed into this update function, and you handle that to produce new state. So the idea is all your data is flowing in one direction, which ensures that you handle it and that there are no surprises in how state might change in your application, like you might find in maybe the old jQuery spaghetti days where data is just stuffed all around the DOM. So I want to just shift gears now and kind of dive a little into that. And we're just going to work through a few simple examples just to see how to interact with the Elm architecture and the benefits it provides. So to start off, let's just look at a very simple static application here. And so what we have here is just some text that says hello world, very basic example. So every Elm application needs a main function, or constant really in this case. And I'm going to set it equal to just this HTML type, which is how Elm represents virtual DOM. So this text function comes from Elm's HTML module. Elm has a built-in module system, and it expects a string, so it's just going to create a text node for us over here with hello world. And I can change that to say hello, Fluent, and have that update over there for me. Now we can also do just normal HTML tags. So I could pull in a strong tag here, and I'll explain the syntax in 1 second. So I can save, and now we have this strong tag with the hello world in it. So most of these HTML functions in Elm take 2 arguments. They take a list of attributes, that would be like class, ID, etc., and then a list of children elements. And so that's how I can start to nest these things together and compose these elements. So I could also add in a div tag here. And so I can have that text hello world in there, and then I can add another tag, a div tag with welcome to Fluent. And save that. There we go, and it shows up. So we have the strong tag and that other div tag that I created. So you can just keep nesting these as much as you need to build your Elm applications. And most of these HTML functions are going to have this same signature of the 2 lists. So now let's look at how we kind of deal with state and really look at that Elm architecture that we saw earlier. So I have this counter application, which has this value 0, and I can increment it or decrement it. And this is like the quintessential simple example for introducing the Elm architecture. So my main function here is going to be a little more complex. Instead of just being virtual DOM, it's going to be something called a program. And when I want to create this program, I give it a record, which basically describes what my model is, what my view is, and what my update is. So model is going to be my initial state. I want it to be initially 0. And then view and update are going to be how I want to display that state and how I want to update it. And I'm basically giving all the pieces to the Elm runtime, and it's going to call these functions on my behalf. So for the view layer, we've already seen how we can deal with HTML tags. Remember, Elm's going to call it, so it's going to provide me that integer value, my current state. And so I have the couple buttons, and then this div tag, which contains the actual value that it is currently. So when I click that, and it goes through the update process, it'll recall my view function. I'll produce new virtual DOM, and it'll know to only update this piece right here. It won't have to re-render everything. Now, what's happening here with the buttons, though? We're actually now using this list here that contains attributes. So in Elm, everything, again, is pure values. So I'm using this onClick handler, which comes from the HTML events module. And when I call onClick, it's a function, I provided a value that is going to be that message. I mentioned messages, kind of like actions, that's going to need to be dispatched on my behalf. So when I click on it, it'll dispatch that value for me, and I know how to handle it in my update function, which we'll look at just in a second. But Elm will handle the actual JavaScript event listener that it wires up for you, and then Elm will know to provide whatever value you tell it when that click event happens. So I'm getting these from a union type, we've seen those, and I'm creating a message union type that can be either increment or decrement. And what this allows me to do is essentially I'm codifying what are the types of state changes that can occur in my application. I don't have to worry about random event listeners or other things like we might see in the DOM just randomly changing my state. It's all consolidated, and I'm saying here's the only way state can change. And I handle that through this update function. So Elm will call the update function with whatever message was dispatched along with the current state, and much like the reducer from Redux, I can use my case expression on the message and inspect if it was increment or decrement and update the state appropriately. So when I click increment, Elm will dispatch that increment message for me, and I can handle it. And again, the wonderful thing about this is if I comment that out, it's not going to compile. This case does not have branches for all possibilities, so it's going to know if I'm not handling all of the messages that I defined in my application. Finally, as we get close to wrapping up, the last thing I want to look at is how to deal with HTTP in Elm, because there's important things we need to consider here. We've been talking about Elm being this pure language, but at some point we're going to have to do side effect type things like HTTP requests. So I have this little sample application here which loads cat GIFs from an API that I built. And it's going to pick a random GIF. And what it's going to do, when I click the button, it's going to send me down some data here from a JSON payload. So I have a data property and an image URL property, and I need to get that image URL. This presents some interesting challenges. I need to make this HTTP request in a pure manner somehow, and I need to get this arbitrary JSON data somehow into the safe world of Elm types. So I'm just going to briefly kind of show you how we approach that. We don't have time to really dive through the entire application, just to give you the highlights of how we can do this and why it's really important. So again, we're going to have a main program here. We're using a slightly different function here. But instead of just providing initial state, I'm going to provide something called init here. And so init, I'm going to use this data type called a tuple. We didn't really talk about that, but you might be familiar with it from other languages. And it's kind of like a list, kind of like a record, in that it allows me to group together multiple values, but they don't have to be the same type like a list. In this case, Elm expects you to provide a tuple when you want to do something called a command. So it's a way for me to not only give Elm my initial state, right here, but also to give it a command, which we represent with a CMD type. Commands are how we actually do side effects in Elm. So they are pure values that we create in Elm because we only have pure functions. But they are sort of like instructions for the Elm architecture. So a command allows me to tell the Elm architecture to make an HTTP request on my behalf, while I can still write pure functions. So I give it the initial state, and I use this getRandomCatGIF to create the command. Down here, where I actually define it, what I'm doing is I'm using the HTTP module to create a request and to send it. But when I send it, I'm not actually sending it myself. Elm's going to send it for me. All I'm doing is producing that command like I mentioned. So I use the HTTP GET with a URL and something called a decoder, which we'll look at next. And then I'm going to provide that with piping into the HTTP send function that creates the command. I also give it a message value. That comes from my union type message in this particular application. And it's a way for me to tell Elm, once the API responds with a value, I'm basically telling Elm, here's how you get out that JSON value I need, the URL, and then wrap it with this new GIF message that I'm providing you so that I can handle it in my update function. So I can do all this with pure functions, and Elm takes care of all this side effecty stuff. Now this decoder is the way we handle that issue of dealing with arbitrary JSON that needs to somehow come into the world of Elm and static types. So this decoder here, there's a lot of helper functions built into Elm's JSON decode library. But what I'm saying is, look for this path, data and image URL, like we saw in the networks tab just a minute ago. And I'm saying it should be a string. And that is going to match up with the fact that I need a string URL, which means if I messed up and accidentally did an int, it wouldn't compile for me. So it's going to make sure that I'm rightly setting forth my expectations of what that value that comes from the API needs to be. So I can fix that. And it loads. Another nice thing is, remember, this needs to be image URL. If that API ever changed on me, or if I mistyped it and I tried to load it, I can handle that error. So if we go up here, when that new GIF message comes in, when the API responds, it's wrapping the result in something called a result type. It's kind of like a maybe type. It can either have an error or a successful value, so it's like a success-fail scenario. But now I can provide an error message if, say, the API failed, like a 500, or if I, in this case, do not have my expectations of what the property name should be. I'm saying image URI, but it's actually image URL. And again, the benefit of this is I have to explicitly make sure I handle this error. If I don't, again, Elm won't compile. So Elm will make sure that you are taking into account that APIs can fail or that API payloads can even change. And so it's doing a lot to safeguard you, even when you have to deal with this very side-effecty, dangerous world of JSON and APIs. And just to make sure everything compiles and works properly again, there we go. Lovely. So just to finish wrapping up, we've taken like a very high-level overview of a lot of the benefits of Elm and some of its syntax and how to even build applications. And I just provide some URLs here. These slides will be available online, but feel free to take a quick photo if you like. But some URLs that help you get started: elmlang.org if you want to start looking into the language, elmlang.org examples. It has the 3 demos I showed you today are actually available on there as well, so you can look at the code as well as plenty of other examples. And then the Elmlang guide and Elm tutorial are great for walking you through how to start building your own applications with Elm. There's also builtwithelm.co, which has lots of examples of really awesome apps that people have built with Elm. And finally, if you start diving in and learning more about Elm, there is a wonderful Slack team where you can come in, ask questions, and get a lot of good help for learning more about Elm. Thank you all so much for joining me today. I really appreciate your time and attention. Thank you.